All right, line V1, learning task 1, where we are going to go and describe manual motor starter features. And this is going to go and start out with a description of something that looks like a light switch. And we need to go and start to disassociate ourselves with what we may have learned about regular switches. And we need to go and take a look at what is it we're actually trying to go and control. This whole line, V1, that we're going to go and be inside of, is all going to go and be to do with motor starting and motor control. So let's go and talk about what a motor actually is. A motor, at its most simple sort of form, is going to go and be a transformer, which is also just an inductor. Half of a transformer is an inductor. That is going to go and receive power from my supply. So I'm going to go and drive current in and through here. It's going to be AC. It's going to be going in and out. As that goes through there, we're going to go and create magnetic flux. That magnetic flux is going to go and cut across to the center part of the motor. And inside of the center part of the motor, we are going to go and have another winding. That winding is going to be built on a rotating part of the motor. We call that thing the shaft. We call the entire center part there the rotor of our motor. And all that magnetic flux is going to go and cut across to this one over here. This winding that we have on the rotor is going to be short-circuited. In other words, it's going to be built with a very low amount of impedance. And so what we're going to have is we're going to have circulating currents that are going to be built inside of here that are then going to go and create their own magnetic fields. Okay, so we've got amps, we've got turns. They create their own magnetic fields. But we know that anytime we've got magnetic fields, those magnetic lines of force cannot go and cross. Instead, those magnetic lines of force are going to go and repel each other. They're going to act like they're elastic bands. And so all of these magnetic lines of force that we are going to go and have on this section, the rotor, are going to go and get repelled by the magnetic fields that are going to be on this section, the stator. And we end up with a slingshotting effect where I'm going to be continuously pushing this rotor along with some of my magnetic lines of flux while simultaneously attracting it in on the other side. Now that is all going to be explained to you once you hit third year. That whole motor effect and everything like that. But what you need to understand for now is that there is going to go and be a current that is going to be pulled out of here. It is going to be an inductive type of current, and it is going to change based upon the amount of speed that my motor is going to go and operate at. If my motor slows down, so the motor itself starts to go and slow down, what I'm going to go and get is I'm going to go and get an increase in the amount of current. We're just going to go and diagram this up top here, or not diagram it, but as far as words go there. So if my RPM goes down, what I'm going to go and get is my current for my motor. We're actually going to replace that with a new term. We're going to call that my FLA, my full load amps, the amount of current that's going to be taken by my motor. This is a term we use all the time. My FLA is going to go up. And as a result of that, we need to go and compensate for that. Now, if I've got a lot of FLA, a lot of current that is going to be flowing through there, I'm also going to go and get an increase in my watts, right? Watts are equal to I squared times R. So if my current goes up, my amount of watts that my motor is going to be dissipating is going to go up. This is not watts, horsepower that's going out to the actual load. We're talking about watts that are now going to be coming off of the motor itself. And this can go and cause my motor to go and overheat. So we are going to go and have to protect from that overheating that we are going to have. So what we're going to go and see is we are going to go and see specialty controls that are going to be watching the FLA. Okay, we're just going to go and set up some solid control components that are going to be watching that FLA. If the FLA goes high, they'll allow it for a little bit, because when we initially start out a motor, that motor is going to be obviously at its lowest amount of RPM, which would mean it's going to be at its highest amount of FLA, which we just refer to that as inrush. We start a motor, there's a crap ton of current that's going to go and exist just for a second, and then the motor comes up to speed, and as the motor comes up to speed, the FLA would start to go back down. We have that upon startup. So we cannot, just react instantly as soon as we see too many amps. We have to kind of allow for the motor to do its thing. If, however, the motor is doing its thing for too long, which is usually going to be caused by just too much mechanical load, people are bogging the motor down, then I want this device that's going to be watching my full load amps, my overcurrent device is what it's going to be called, or my overload device, actually, it is a form, is going to go and respond to that, and it's going to go and shut the motor down. So that's what all of our motor starting equipment is going to need to be able to do. It's going to need to be able to handle the inrush, that huge amount of current that happens when we start out, when we're at 0 RPM. And it's going to need to be able to go and monitor to go and make sure that my motor itself is not going to be running hot for too long. Some motors do have overload protection that is going to be built into the motors itself. You might have seen these on single-phase motors before where they got a red button that's going to be on the motor control box. That red button is just designed to go and, activate that. Okay, so let's go through the components that are given us. The very first learning test that we have over here is going to be manual motor starters. Manual motor starters means that they cannot be operated remotely. A human actually has to walk up to them and do something. Flip a switch, in this case over here, or push a button, in this case over here on a push button starter, or if they have to go and turn a handle, in the case of these drum switches that we are going to have over here. For all three of these, the actual contacts that are going to be making and breaking contact are going to be inside. This one over here, we are going to go and have L terminals, L1 terminals. We're going to go and have T1 terminals that we're going to take out the bottom. Could be a single pole device. It could be a 2-pole device. We have 3-pole devices as well for our 3-phase motors. They look like standard switches, these ones, but they look like super beefy, heavy-duty ones that are going to be inside of there. They do have an overload protection. That's the reason why they look so big and beefy, is because there's more components that are going to be inside of there. That overload protection is simply going to be a component inside of there that is going to go and monitor the amount of current that's traveling through. And if the current is too much, it's going to heat up, and then it's going to go and cause a mechanical activation that's going to go and pop that switch back open. If we do trip one of these off of an overload, so the motor is pulling too much current, this thing senses it, allows it for a little bit, then says, okay, that's enough, shuts it off. What's going to happen is it's going to act like a circuit breaker. This handle is going to go and move in some cases. Other cases it stays high, but you just have to wait for it to cool down, just like a circuit breaker. And then you got to move it down to the off position and then back to the on position again. These ones over here, the mechanical push button starters over here, do not have a way for us to go and wire in remote push buttons. Okay, we cannot go and add in push buttons that are going to be somewhere out in the field. Everything off of these ones is a mechanical push button. Really, it's just going to be a teeter-totter that we're going to go and see. If I took a look at it, I've got 2 of these over here. These are going to be set off of a fulcrum inside of there, and so when I push down on the one, we call that thing the start, then the stop is going to go and push up and out. And if I push the stop, then the start is going to go and push up and out. So whichever one we press is going to go flush. In this case, the start, it's going to be flush with that one. And the one that is, waiting to be pressed is going to go and be raised. It's going to be proud of the surface, as we would say. So that's the way that these ones here are going to operate. Once again, same type of thing as before. We are going to have current monitoring that's going to happen inside of them. The one manual motor starter that does not have current monitoring inside of it is going to be this thing, my drum switch. Now, a drum switch is going to be a rotary selector switch. This one over here shows a load of contacts off of it. Most of them don't have this number of contacts. Our most common ones are really only going to go and have 3 drums of contacts. So we would lose these ones down here. We're going to go and have contacts on the sides, and there's going to be wiring diagrams that are going to be associated with them. Drum switches are used, generally speaking, for reversing of a motor, or occasionally they can be used for speed control if I've got a specialty type of motor that's got 2 different windings on it, for 2 different speeds. Not as common anymore. We mostly do speed control through variable frequency drives at this point. Each of my contact switches inside of here are going to be rated to go and interrupt and make that inrush current, so we're going to call them horsepower rated contacts. But they're not going to provide any sort of overload protection. You would have to go and wire from this down to some sort of an overload protection before you go off to your actual motor itself, somewhere out in the field there. This one here is a very large one. Most of the ones that you will probably run into are going to be these smaller ones. This is a very popular one out in our industry. It's the Square D AG2 drum controller. Very compact, and it's got a handle up top there that can be taken off, and it can be flipped around, and you can go and use this thing. So it's either a momentary, where somebody has to stand there and push it into position to hold it, or where it could be a maintained, where they can go and shove it into the forward position or into the reverse position and then walk away from them. Inside of a drum switch, what's going to happen is we're going to go and have an off position. That's the central one over here. Inside of the off position, you see that there is no contact made whatsoever with any of my lines. When I go and put it into one direction, to my forward over here, I'm going to see that I'm going to go and make contact with some of my lines over here. There's going to be a connection from 1 to 3, and 2 to 4, and 5 to 6. When I reverse, 1, instead of being in position number 3, switches over to number 2. And this connection, 2 and 4, that we had before, switches over to number 3. And then this connection over here, number 5 and 6, gets made again. In reality, these ones over here are acting very similar to the way that we look. It's a different way of diagramming, but you could go and re-diagram these things. They're acting very similar to the way that we look at what we refer to as a four-way switch that we use for controlling lights, right? Where it's just going to go and crisscross the connectors that we are going to go and have. If you wanted to, you could just draw this thing out as that. You could call this thing here 1 and 3. And then you could go and reverse this one here and call that one 2 over here and 4, like that. And it's going to kind of give you the same sort of operation that we would go and have. 1 and 2 can make contact, or 1 and 3 can make contact. 2 and 4 can make contact, or 3 and 4 can make contact inside of there. It actually would be much more handy inside of these boxes if they would draw them as that, if they would label the contacts like that and just draw that like that, because most of us as electricians are pretty used to that idea. But we'll talk about making the connections to the motors later on when we actually start dealing with reversing a motor. Right now, just understand that contacts inside of here are going to go and reverse my current flow. We're still at the describe, not yet at the operate. All right. Overloads. Okay, we are going to learn about overloads properly because there are so many people that do not understand overloads. And then they come back in third year and we talk about overloads and they try to treat an overload like it's a switch. And then they come back in fourth year and they try to treat an overload like it's a switch. And then they leave and they still don't understand it. So this is your first introduction to overload, so we are going to do this properly. An overload is designed to sense heat inside of my motor. That is all that the overload is designed to sense heat, or is designed to do, is sense that heat, and then it is going to use that heat to go and trigger something else. The overload itself never actually opens. I want you to just repeat that out loud. The overload itself never actually opens. What it does is it sends a signal for something else to go and operate. Okay, let's first start with what the overload heater is itself. This one that we have over here is what we refer to as a solder pot overload. And we're going to go and bolt this thing in line with my motor control. So somewhere upstream, I've got my switch that is going to go and control the motor. And then I'm going to go and bolt this thing in. These are just copper pads over here. And then I'm going to, from here, carry that out to the actual motor itself. So all of the motor current is going to go and flow through here. What's it doing inside of here? Well, inside of here, there's going to be, and this is a card, you can't really see it, but it's a wrapped around bunch of heater wire that's going to be inside of there that goes out to there. Do you see how that is a continuous piece of wire? Is there any switch inside of this whole section over here in the way that I have drawn it right now? I want you to look at that really carefully. Is there any switch? No, there is not any switch. There is a continuous piece of wire. Okay, so this overload is never going to actually separate over here. What this overload is going to do is it is going to go and take a look at the current that is coming in. So we're going to close this switch over here at this point. And when we close that switch, now there's going to be current that's going to be able to go and flow through here, flow through each of these, and go out to the motor itself. I know we're not drawing in the rest of the motor lines. We'll draw in another line over here. We'll take that there. That's going to be my neutral coming back out. So we see all of that current is going through there. During normal operation, the heat that's generated off of this is going to be inconsequential. Not a lot of heat that's going to be coming off of it. But once we start to bog the motor RPM drops. It's the first thing that happens when the motor is going to go and get bogged is the RPM is going to go and drop. What happens when my RPM drops? My FLA, my amps, are always going to go up. Doesn't matter what type of motor we're looking at. My current is going to go up. So now I'm going to go and have an increase in current. We'll draw some double arrows here now, okay? We've got an increased amount of current. Double arrow up everything that we have over here. This is not going to go and activate instantly. It's going to go and start to heat up. You know, you've probably seen stovetop elements before. The second you turn them on, they don't go red hot immediately. They take a bit to go and heat up. Same with what's happening inside of here. So it's going to start to go and heat up. If it gets hot enough, it is going to go and trigger this little disc inside of here, which is going to allow that disc to spin. Note that the wires do not open itself. The spinning of the disc itself, the physical, the mechanical activation of the disc itself, is then going to get applied to the switch and pop that switch open. That is what an overload does. If you did not get that, review the last, I don't know, about 5 minutes that we just went through there and watch it again. What you need to see is that the overload itself stays intact over here, okay? That never opens up. It is just a heater, a little tiny baby heater that is in line with the motor itself. All right. Two main types that we do have are going to be either this one here, that's going to be what we refer to as a solder pot one, where we are going to go and have inside of there, I'm going to erase all of my lines now. You understand what's happening. Inside of here, we are going to go and have solder that is going to be around that canister over there. The solder is normally going to be solid, but solder has got this property called eutecticness, and they write that out over here. Eutectic means that it goes very suddenly from being being solid over to liquid. So once we get it up to within about a 3-degree span, it is just going to go and change immediately. If this thing is solid inside of here, this little wheel cannot go and move. But if this thing turns into liquid, obviously this wheel would be able to go and move. So what we do is we jam that wheel up against something. We want to take a look at this one over here. This one shows up later on in your module. I prefer this one because this one is screwed. Okay, we're going to take a look at that one. I'll tell you why it's screwed in a minute. But we're going to go and take a look at this itself over here. Okay. Inside of here, what we're going to have is we're going to have a small set of electrical contacts. That's these ones that we see right over here. These ones have got a spring that is giving them an upward force on there. And they're making contact right now so that current can go and flow through here, through them like that, and back out over here. This is going to be my control circuit. Okay, just write that out over there. That's the control circuit that we are going to go and have. This section up top over here is the actual motor. Let's take a look. See, it's big, beefy conductors that we have coming in here. The motor current is going through here, and it is going through that little heater that is up top over there, and then it is going back out over there. If this thing gets hot enough, that solder pot is going to go and melt because I've got upwards pressure pushing on this. All of a sudden, this component over here, which is stuck up against that little wheel, is going to be able to go and push up. And when it pushes up, what it is going to do is it is going to go and separate this circuit that's going to be down over here. Okay? So there we are. We're going to go and push that up. It's going to go and separate that circuit. When it separates that circuit, it will break that contact that we have in the middle over there. Just completely wipe that out over there. So we've now broken that actual contact to our control circuit. Note, once again, that what happened inside of my overload is not that the motor current itself got interrupted by this. What it's going to do is it's going to go and ixnay the control circuit over here. It just takes that sucker right out. And as a result of that control circuit being shut down, that is then going to allow us to shut down the motor. Okay, we're going to have power circuits for motors and control circuits. All right, let's talk about this hairy thing that they have up top over here. What they're showing you up top over here inside of this one is basically the same thing as this color diagram that they have down below, but the problem is that they show a connection that does not exist. That is this connection right over here. We don't have that connection that we are going to go through and operate that thing inside of these things. We are going to go and use these overloads separately from what we actually have inside of the control circuit. So this line over here should be gone. What we should see instead is just, once again, going to be that my motor current is going to come in. It is always going to be able to travel through my heater, and then it is going to go out to the motor itself, and then we are going to go and trigger a control circuit with this. This does not go to the motor over there. That one should just be going to my control circuit. Inside of our manual starters, they're going to have that already pre-wired so that you don't have to go and do that. They're going to go and have the overload. The overload has got a symbol that we are going to be getting used to seeing, and that symbol is going to go and look like this over here. That's going to be my symbol for overload inside of there. That overload inside of there is already going to be mechanically linked. We're going to just draw a dotted line like that to that actual switch so that if we go and pass too much current through this, when it's in operation, this is going to be able to heat up and it's going to activate the switch. But this itself, the overload itself, is never, ever going to go and open up. Okay? I hope you are getting this, because it seems to be such a big disconnect in our industry. All right. The other style that we have is going to be the bimetallic strip. Bimetallic strip is going to be made up of two dissimilar pieces of metal that are going to have different rates of expansion that are going to be epoxied together with a super high strength epoxy. What happens is that as this would go and get heated up, so once heat transfers over to these, that is going to go and cause them to bend. And they're going to bend and expand at different rates. The one that expands less is going to go and form the bottom of the curve. The one that expands more is basically forming like these little wedge-shaped pieces out of itself, and so it's going to go and form the top of the curve. What we can do is we can use that bending of that metal strip to go and trigger something. I don't know if you're much familiar with doing baseboard heaters, but if you have done baseboard heaters, you've probably seen thermostats before, and inside of the thermostat, I'm just going to draw this out because the thermostat is a great use of those bimetallic strips. Inside of your thermostat, you're going to have this thing with the cover off. There's usually going to be a big piece of metal that's going to be across here, and I forget, this might be a Newtone one or something like that. I can't remember which the manufacturer is, but it's got this big piece of metal, and across that metal, there it says, do not touch, do not touch, do not touch. They printed on there. And people seem to think that that's going to be a live piece of metal. It's not a live piece of metal. Look at the amount of holes in that thermostat cover. There's no way we could have a piece of metal that big, that live, where tiny little baby fingers could go and poke into that thing. What that is it's a bimetallic strip. Next time you look at one of these, just take a pause at what you're doing and look at it sideways. You'll actually see the two separate, well, depending on how good your eyeballs are, but you should see the two separate pieces of metal. This piece, the reason they don't want you touching is because they don't want you pressing up against it. Because if you press up against it, you're going to bend it, and then you're going to have mechanically distorted it, and all of the temperatures that are going to be on here are going to be out. People might be trying to set this thing for 20 degrees. Instead, it's going to be going to 25 degrees because you touched it. You bent it. That's why they don't want you to go and touch it. But inside of there, that bimetallic strip is actually, it's anchored on two sides. So it's only got the option to bend up, or it's got the option to go and bend down. But that bimetallic strip is being utilized to go and operate. In the very bottom of that, there's going to be a little micro switch. That's where the actual current is going through there, is inside of this little micro switch. For your thermostat over there, it's going through that little micro switch. When this thing goes and bends out, it's going to open that. When this thing goes and straightens out, it's going to go and press down on that one, and that's going to go and operate our circuit. That's a bimetallic strip. It is commonly used for temperature sensing. We will use these things inside of a circuit breaker. We will use these things inside of our motor overloads. We use these things inside of our thermostats. They're not fast acting. They're relatively slow. We're talking about distortion of these materials. So they provide a little bit of a time delay. Looking at this is our bimetallic overload relay. They give us the actuating bimetallic up top over here. Then this thing is going to go and have an insulating link that is then going to get attached to our trip bar that we're going to have over here. What I want you to just follow through is the motor connection itself. So the motor connection itself is coming into this thing. It is going up that center over there, and then it is winding around itself like that, and then it's coming back out, and it's going to the motor. That is the path of motor current. If you take a look at that, you should see that once again, that is a continuous piece of metal. There's no switches inside of that thing. It is just a heater conductor. So I'm going to be able to pass my motor currents through this thing out to my motor itself. It goes through there, causes this thing to heat up. Normally it's going to be just kind of idling along, low amount of heat. But if I'm going to go and once again slow down my motor, I drop the RPM, my FLA is going to go up. And because my FLA goes up, this thing is all of a sudden going to get too hot. And as it gets too hot, it's going to go and introduce that heat into the bimetallic strip. The bimetallic strip is going to start to go and bend. And what the bimetallic strip does when it bends is it pushes down on a little bar over here and it opens up this circuit. Take a look at how those two blue conductors over there are not connected. Normally, this is going to be closed. It's going to be my control circuit. Note how this one does it properly. Shows the control circuit separately from the motor circuit. One thing that you need to be aware of for both of these is that they're going to be temperature dependent, which means that whatever the ambient temperature is going to be is also going to go and lead to these things, tripping out. If you place these in an area where it's super hot, these are going to go and nuisance trip. If you place them, right above a heater, they're going to go and nuisance trip, and the customer's not going to have any idea why. They don't know it's because you got that thing over top of a baseboard and you're just, dumping heat up and onto it. So be careful with where you place these things. Inside of our code book, we're actually going to be required to go and place these things in the same ambient as what our motor itself has. You cannot go and have your motor operating in, a 50-degree ambient. Maybe you got up high in a boiler room or something like that, and then that you're going to have this, somewhere else, because they have to be, tied together. They need to be able to go and sense the same ambient as well as the current. It is a misunderstood component of overload protection that they should be in the same area. Okay, resetting these things is usually just going to be done off of a little push button that is going to be popped out. When we have got the solder pot type over here, when that solder pot is going to go and activate, and I'll just go and grab, I'll grab this one over here. When this solder pot goes and activates, this bottom part is going to go and pop up. When that pops up, there's also going to be another mechanical linkage that's going to go and pop up on the surface that we are going to go and have. When that surface pops up, we wait for this thing to cool down, then we can push it in and reset it. In a lot of our components that are out there, what we do usually see off of these ones is a blue button. I don't know, it's just kind of this kind of industry standard that a lot of our resets for the overloads have been these little blue buttons off there. For anything where we're going to go and pop the button up, you can expect to go and see that. For ones like this where we're going to have our push button starter, then the stop button is going to go and automatically pop back up and out of there. And for these ones over here, it's sometimes going to move to the center position, just like what you would have off of a circuit breaker. Other times it maintains the on position, but it feels sloppy. Like you can feel there's no mechanical linkage that's active at that point. What you need to do is you need to go and take that thing down to the off position, and then you go and move that one back up to the on position once again. All of these starters that we have so far looked at are mechanical starters. And mechanical starters just require us to go and do the resets ourselves. They're not going to go and automatically reset. They're also going to go and provide us with this other, I guess it's a operational state that's not always going to be desired. And that operational state is going to be automatic restarting. If I flip this switch into the on position and I close that, now I'm going to go and have my motor that is going to be operational, and that's going to be fine. And then, if you get one of those days where the power goes out, particularly if the power goes out about an hour before, whatever your factory is supposed to go and shut down, usually they'll say, well, we'll wait around here for 15 minutes, and if it's not back on, we'll just send everybody home because, we're not going to get restarted. What happens, though, is that you've got a bunch of stuff that is going to possibly come back on automatically. Your operator will not necessarily remember that this thing is still switched on. It's mechanically turned on at that point. And they're going to go and walk away from that, and then the power comes back on later on, and this thing is going to go and restart. You have to be very careful with these type of devices that you're not going to put them onto something that is going to, if it automatically restarts when somebody is not around after a power failure, is going to cause issues. Okay, that's going to be a really dangerous thing. In some types of equipment, it's fine. Fans and blowers that they give us over here, pumps that they're going to go and have, particularly like sump pumps or things like that. As long as you're not going to run it dry, you should be fine. But for other stuff, where either there needs to be process variables, stuff that's going to be run through there, they need to have water inside of some pumps. They can't run dry. Things like that, we would have to be very careful that it does not go and restart. This is going to go and be called release that we have over here. We're going to talk about that again later on once we start seeing our 3-wire controls, the difference between low voltage protection and low voltage release. But for release, all that release means is that it is released to start again. These manual starters provide low voltage release. This one here, where it's got the lever type of buttons, and these ones over here as well. Okay, let's talk about ratings that are going to be on these. All of these are going to go and have ratings that are going to be specific to the fact that they're designed for motors. We cannot just go to anything that has got a voltage and a current rating, voltage of 120 volts, current rating of, let's go and say 12 amps off of that thing. We can't just grab anything like that that is rated for the 120 volts, 12 amps, and say, well, I've got a motor over here that is going to be operating at 120 volts, and that is going to be operating at 8 amps. Because if I grab that motor and place it onto there, there's going to be some catastrophic effects that are going to go and happen when I go and start this motor up, or if this motor would go and get to what we refer to as a locked rotor or a stalled type of position. Generally speaking, our inrush is going to be about 3 times the ampacity, 300% that we say. So for, point of reference, anytime that you're looking at a motor, you're going to take that, you're going to multiply that by 3, and we're going to say that our inrush is going to be 24 amps. A regular switch rated for, 120 volts, 12 amps is not going to be able to handle that 24 amps. It's going to go and get destroyed when we close in on it. It's going to get destroyed when we pull out of it. Maybe it'll be fine the first time or two that you do it, when you as the electrician wire it in, flip it on or off a couple times and say, yep, looks good from here, and then leave. Yeah, you haven't done enough damage, but it's not going to last. This is why we have got what is referred to as horsepower ratings that we are going to utilize, because horsepower ratings basically mean that these things are going to be designed to handle inrushes for certain motor types. Our main ratings that we are going to go and see off of these are going to go and be the voltage, which is going to go and talk about the voltage of the motor itself. So here we've got a starter. We're given 2 different voltages that we're going to go and have off of there. We are going to go and have ampacities. Now, ampacities are usually going to be given as a range. This sheet over here does not show us the actual range, but it's going to go and tell us that this thing could be a range of, 0 to 12 amps. We don't know which one it is because we still have to select the overload itself that is going to go inside of it. The overload itself that would go inside of the switch is going to be done off of one of these types of charts. These charts are usually going to be listed on the inside of the actual enclosure so that you don't lose them, and they're going to be given you as, part numbers inside of there. What you're going to do is you're going to go and take a look at your motor. Let's go with that 8 amp motor that we had there before, and you are going to go down the motor full load current. So that's 2 of the same. So you're just going to go down that one. Nope, I don't see anything good for 8 amps. You're going to go down this one. Oh, right over there. There's one that is good for 8 amp. And so what I'm going to do is I'm going to go and say my motor current is 8 amps. So I'm going to go and get the heater, the actual solder pot heater that has got the part number GGH 9.7A that is going to be utilized. And I'm going to take that and I'm going to bolt that in. See how this solder pot heater over here has got actual, let's erase this, bolt holes. What it's going to do is inside of my starter, there's going to be a place where this thing is going to go and bridge a gap. Okay, the one side of the gap is going to go out to the actual motor. The other part of the gap goes up to the actual switch, the way that we had it. And we take this that we have over here, and then we bolt it in. Well, I actually screwed it. Usually it's just going to be done with big machine screws over there. We're going to go and bolt that thing into this. Those are screws, not a no symbol. Just draw some Robertson heads in the middle there. We bolt that thing into there, and it has to be the proper rated one. It should always be identified on them. So that's what we're going to do inside of here. We're going to go and select the proper overload based upon the motor amps. If it's not going to be inside of that starter, use the internet. You can look those things up. Let's talk about the horsepower rating that is off of these ones as well. The horsepower rating is going to be different based upon the value of voltage. So over here, if I take a look at my value of voltage, a certain starter, this starter over here, the B300-9115, it's a manufacturer-specific part number. It's not like a general thing you need to memorize. But for that specific starter, at 120 volts, we call 115, 120. It's a nominal rating. We can only go and use 1 horsepower. If I go up to 230 volts, I can go up to 2 horsepower. Wait a minute, this doesn't make sense. For this size, it's a size 0 starter over here. Why can we only do 1 horsepower at a lower voltage and 2 horsepower at a higher voltage? I want you to just go and think about this as if it were amps. Okay, 1 horsepower would be 746 watts. 2 horsepower would be 1492 watts that we would have over there. If we take those values and we divide them out by 120 volts, I'm just going to pull up this calculator here a second. We're going to take the first one there. 746 divided by 120, we get up to a value of 6.21 amps. So really what it's looking at is, 6.21 motor amps that it's going to be able to interrupt. And if I use this thing on 240 volts, where's that calculator gotten off to here? 1492 watts, that's 746 times 2 horsepower, divided by 240 gets me up to a value of, would you look at that, 6.21 amps. In other words, these things are amperage rated. If we go to a 241, that just means that we are going to still have the same amount of amps. That's why we like to go to, 240 volt. We can get more horsepower out of it for the same amount of amps that we're seeing. So that's why these things have got a lower horsepower rating at a lower value of voltage, because really what we're seeing is that this thing, the contacts that are inside of it, are built for 6.21 amps that they're going to be able to interrupt of. Motor inrush, they're going to be rated so they can take 3 times that, a good 18, almost 19 amps that they can take during inrush, and that they're going to be able to interrupt that as well when they go and, trip out. Okay, be very careful with those things. Always make sure that the horsepower that you are selecting is matched to the voltage that you are going to be working with that thing at.